I start with in the beginning. Okay? And then the question is, one of the things you wind up doing is, if you start with very big network, you can't go wrong in the sense, in terms of capacity, but it might take too long to train that network, and it might also get overflow. So you're better off starting with smaller networks. But then the worry, of course, is if the smaller network is too small, how do I know? When am I supposed to learn a bigger network? Okay, so there are two things that help you, which is validation error and training error. So remember, if you have a whole bunch of data, training data with labels, you first split it into two pieces. We call this test, and as I said, if you remember, the test data is the one you put in the Coca-Cola bottle. You never touch it, like never, like ever. Okay? And then you have this stuff that you can play with during training. You split that into, this is the actual training data, and this is the validation data. So what you're winding up doing is, you train on this training data, you test the error, loss error, on the validation data. And then if the validation error is too high, then you might try a different configuration of the network. Because there is an indirect feedback loop between the validation error and the training error, eventually validation error actually seeps into the network, because you're learning from the validation error. Training test error, test on the other hand, is kept separate, completely separate. Because nobody unfortunately gives you the future and say this is how the future will be. You see what I'm saying? Okay, so now that we remember that, so then given the validation error, so one thing that you basically do is anytime you are running these networks, any learning algorithm, you essentially keep track of two kinds of errors. One is how much of the error, what is the error on the training set, I do that in the blue, and what is the error on the validation set, I do that in green. In the first case, as amount of data, amount of training, number of times you are updating the weights are increasing, then in essence, this is the best I seem to be able to do. I'm getting the validation error to something here, maybe that's like about 40%. If you're happy with 40% error, it's okay. If on the other hand you want to drive it down to 0, then in essence it means that the network you started with doesn't have enough capacity to even memorize, to even learn the training data correctly, let alone fixing the future data. So then, when this happens, you will wind up increasing the size of the network and relearn on the same data. When you do that, maybe next time around, you will get training error close to 0. Okay? That basically means at least the network has the capacity. If nothing else, it can just memorize all the data. The real question is there overfitting going on? Is the network somehow actually memorizing instead of learning patterns? There is no way of telling other than checking how it is doing on the validation error. And the most reasonable thing that most of the times you will find that validation error, as the training error comes down, validation error comes down in the beginning, and in many cases it starts raising. And you should be surprised at this behavior, that training error has gotten to 0, validation error is increasing. The closer you are making the training error, the higher the validation error is becoming. When that happens, that's when you have realized that you are not learning, you are remembering. Do you understand? Okay? That's what is overfitting. If you just memorize the data, then in essence, your performance on the validation data will suck. You see what I'm saying? Remember, going back to my grading example, if I just remember, the grades of 55 students, I have a big enough brain that I remember grades of 55 students exactly. So if it is, this is the social security number, this is the grade. This is the social security number, this is the grade. It's completely useless in predicting the grade of a new student who is not in the original sample. Because nobody has the same, no two people have the same social security number. So I just memorized. Memorizing is another name for overfitting. And the only way you'll figure out you memorized is indirectly this way. You started seeing the validation error is going up while the training error is going down. Yes, sir?
Will the x-axis on those graphs be time in?
So there are two ways of looking at x-axis. One is if the x-axis is sort of proportional to the number of times you are updating the weights. It is also proportional to the amount of data you have. Okay? So in fact, if you don't have enough data, that's another time when essentially, if I only have like 2 examples, there's not much I can do in terms of ensuring that I learned so there are 2 ways you can fail to learn, right? I didn't give you enough training examples for the test. So you have no worked out examples. The other is, I have given you training examples, but you went to a movie instead of studying for the exam. Both ways you will fail. And so x-axis is capturing both of them. Okay? So that's basically, did that answer somebody's question about how do we figure out? So this is essentially how we figure out overfitting. Now, a well-behaved learning algorithm would be such that when training error is going down to 0, test error also, the validation error also goes to 0. So as the training error is going to 0, the validation error also should go to, validation error also should kind of track the training error. If you do that, then no overfitting. So one question that this thing brings up is how do we stop overfitting? Can we come up with learning algorithms that despite their capacity, they have overcapacity and yet they don't overfit? That's actually one of the deeper points of machine learning. How do we ensure that, it's not like you use only a small piece of your brain, for different kinds of learning tasks. Your brain is what your brain is. And yet, you should be able to ensure that you are looking for the patterns rather than memorizing the data. Do you understand what I'm saying? In this particular case, I can try different brains, different neural networks. You don't have that luxury. You only have one brain. And you better learn in such a way that even though, assuming that you have the capacity, which I hope all of us do, you should make sure that it doesn't overfit. That means it behaves more like this than like this. There are many ideas that help dealing with the overfitting problem. Okay? One idea that is particularly interesting in the context of neural networks is the dropout method. And it is connected to a very general idea called ensemble learning. Okay? Basically, this is the idea. The idea is, instead of picking one particular network, imagine you train n networks on the training data. Okay, so n can be 10, n can be 10,000, n can be 10 million. Imagine you picked 100 networks. So you trained 100 different networks with different configurations on the same training data. And they'll have different validation errors. During the test time, rather than just ask one network, you think of these networks as a committee of experts. And in some sense, you aggregate their recommendation about what the class is. Do you understand what I'm saying? So if in fact there are 100 networks, you train them all on the same ImageNet data, let's say, and then a test example comes, some of them are saying cat, 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 some of them are saying dog, 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 some of them are saying, whatever, like a truck. So you count the number of people saying cat versus dog versus truck. And the one that is saying, let's say, there are more people, more of these networks are saying cat. Then you say cat it is. This is exactly what you do when you get a second opinion and a third opinion. You're hoping that committee of experts is better than a single expert. It actually turns out that there's a beautiful theory from Bayesian learning. I mean, I'm building up Bayesian learning like so much that when it comes, there should be rapturous. Bayesian learning essentially captures this. One of the things about Bayesian learning is Bayesians never actually decide which network they are using, in essence. They will consider infinite number of networks. All of them are considered hypotheses and with different probabilities. In the beginning, they might say all these networks are equally likely. As they see the examples, the probability of each of these networks being the true network will be changing. So now you have a posterior probability on the hypothesis space. And when you're given a new example, you use Bayes' rule to figure out what should be the class of this, given that all these different guys are saying different answers for this single example. So when we get to Bayesian learning, I will basically remember to mention that Bayesian learning is an oxymoron. Because somehow you think learning means picking one truth. Bayesian learning says there is no such thing. There are many truths, and you just keep track of the probabilities of each of those hypotheses actually defining your data correctly. Ensemble learning is essentially the reason you don't do Bayesian learning is because it's too costly. For example, you only have one brain. Imagine if you get to have like 1 million brains, and then you put different ones of them and figure out which brain to use with what probability for what task. Instead, since you can't do this, you do the committee of experts. You have one brain, your friend has one brain, your other friend has one brain, and normally the quote-unquote team projects will involve, okay, you do all those difficult integrations, I do the differentiations, and this third guy will do the additions. Right? That's the committee of experts way of splitting your work. And in essence, what you're doing there is Bayesian learning for the poor people. Okay? Now, one version of Bayesian learning in the context of neural networks will, as I said, involve starting with 100 different or 1,000 different networks, training them all 1,000 networks on the data, and then actually keeping all the 1,000 networks, and when a new sample comes, ask all the 1,000 guys, average their prediction. That's what you want to do, but it's too costly. What Dropout does is a beautiful way of approximating that idea. It only keeps one network, but during training, so this is the network, let's say you are using, so you only have one brain, so you only use this, okay? During training, unfortunately you can't do it for your brain, but you can do it for neural networks. During training, with probability P, you just make a particular weight be out of training. So this time use it out. So remember, it's a stochastic gradient. We'll just be doing stochastic gradient. There are, examples are coming one by one. First example comes, let's say I use all the weights, everybody gets each. When the second example comes, then I randomly tell individual a whole bunch of weights. Oh guys, you are sitting out this time. We are not going to change you. It's as if you're all zeros. And then the rest of the guys will be changed. Third example, a new random set of weights will sit out. Fourth example, a new random set of weights will sit out. You see what's happening right now? It's strangely similar to having 100 or 1,000 different networks being trained, one being trained for one example. Looks like a crazy idea. It makes no sense if you don't understand overfitting. And if you don't understand committee of experts. So in the dropout method, this is what is done during training, and in the test phase, you use all the weights. So it is as if many networks were trained, And they all just coalesced into one network for the testing. Imagine the beautiful savings in efficiency. One, you don't have too many networks to handle. Two, during the training, there's only one network. Dropout is one of those great ideas. Just along with the Xavier initialization, dropout is one of these great ideas that made large-scale neural network training actually possible from a theory standpoint. Okay, yes?
Is it just nodes that are dropped out, or are just weights dropped out?
You can do either way. I said weights, but actually they drop the nodes and then drop all the weights for them.
Okay.
So essentially you're doing brain damage, but randomly at every point.
Are weights ever dropped out without dropping the given nodes, or?
No, I think in the way actually, I said weights, but really the weights implemented is you drop out drop out a node. When you drop the node, all its weights are essentially coming out. All the weights coming in and going out are sitting. That's a way of dropping. So the way I'm talking about dropping weights, it's more fine-grained. As if one node, some of the weights will be trained, but some others won't. Here, the entire node sits out this iteration. It's a beautiful idea. It's a superposition of this, so the way to understand this in terms of committee of experts is as if not only do you have 100 networks, but you also randomly select subsets of the examples to train each of these 100 networks. And it works, and the only reason it works, it turns out the best way to say why it works is because it's doing what Bayes said you should do. Don't commit. Those of you who can't make up your mind, you are Bayesian. You see what I'm saying? Coke or Pepsi, you say yes, you're Bayesian. Okay? In essence, you keep all the options. And if you keep all the options, theoretically you can't go wrong. It's the guys who make up. In fact, it's the same thing. I mean, Coke or Pepsi are this person or this person as spouse. And let's have both of them. Believe me, you can't go wrong. I mean, not that I should say believe me, I don't have experience. But apparently you don't go wrong. Okay? There is no buyer's remorse. But unfortunately, if you have too many spouses or too many different options, your life becomes much more complicated. That's why Bayesian learning is not done, because we have small brains. True gods will do Bayesian learning. Yes, sir.
So all the weights are also present for the validation data, right?
That's, yeah, testing basic. Validation is an internal testing. So think about this. I gave you some number of examples, right? So you basically are split it into 3 pieces, and the validation test, you're just checking to see, am I understanding the concept? And the test is representative of what actually happened during the midterm. Unfortunately, you didn't get to see it until the day of the midterm. That's dropout. Beautiful idea. Right? Okay, let's see. Let me at least introduce convnets, and then the way it's going, we have to spend some of our time in the next class also for convnets. I already mentioned that convnets are exploiting structures to reduce the number of parameters. Okay? It's this part of the lecture, convnets, it's really, you assume that data is images. Input data is images. Up until now, data is anything. Right now, we'll assume just images. For images, it turns out there's a particular kind of structure, and you want to exploit it. And this part basically says why you want to reduce the number of weights, which I assume I explained to you already from the Harvard example. You reduce the number of weights, you should be better. Okay? There are many different ways of reducing the number of weights, it turns out. Okay? The ones that I was looking at last time was I kept it, think about this, I kept all the nodes here. Okay, all the nodes here, and then somehow I reduced the number of weights. Right? Try to visualize something that I'm going to try and say here. Imagine actually this level only has these many nodes. And these guys will basically first operate, let's say, on these 4 guys, then the next 4 guys, then the next 4 guys, then the next 4 guys. As if these guys are processing the same input with the same weights. You understand what I'm saying? So it's like these guys will always take, will basically be doing, for each of these inputs, let's say, they will do the same thing. So the first input they'll multiply by 0.7, second input they'll multiply by 0.8, and third input they'll multiply by 0.3, fourth 0.2, fifth 0.7. And when this whole thing comes here, they will do the exact same thing again there. So the same weights they're going to use to multiply. That is a different way of reducing the number of weights. It's as if the middle layer is moving up and down, basically spanning the input. Think of the raster scanning. That's actually not a bad example to have in mind. That's what cabinets do to reduce the number of weights. Okay? Why do they do it? It turns out that before that we did some violence to cats. Google and Drizzle basically essentially kind of connected electrodes into the cat's brain, because currently undergraduate students are not allowed that sort of thing. And then figured out what is, tried to understand the neuroscience of vision at some level. And they kind of found basically what I am saying, that there are two things they found. One is that there is this sort of a kernel structure that basically means the neurons are essentially operating on different parts of the image. The same neurons are operating on different parts of the image. By the way, there is a word called saccade. How many of you know that when you are looking right now, when I'm looking at you or when you're looking at me, how many of you realize that you are not looking at the entire picture at all? At any given point of time, of course you are doing, because this guy is supposed to psychology, and the rest of you basically assume, wow, wait, I'm getting high definition vision. Okay. You have pretty bozo eyes, okay, and the eyes are looking at pieces and pieces and pieces and pieces of the image, and the brain combines them all together and makes it look as if you are looking at this beautiful image, which is exactly why all the visual fallacies come. Because brain is continually, essentially kind of, even though you're currently seeing only this piece, you think as if you're seeing the entire image, because the brain is telling you so. So that's one part. So brain actually works that way. So in fact, there is some reason to believe that this idea of a small patch of units moving on the input at different places and processing them. This processing is called convolution. The multiplying weights by the inputs, basically seen as convolution. And one other thing, of course, is in the example I had, I basically talked about a linear example. The input is all linearly organized. The cells are linearly organized. With vision, you have a two-dimensional picture. So in essence, you have the, let me show you this. So you have the two-dimensional picture, and essentially what is moving here, that's a little convolutional kernel. What it's doing there is, when it's here, for example, it's multiplying this by 1, etc., and it's doing the same weights every time it's moving the filter. When it does that, in essence, the operation it is doing is it's multiplying. So let's, I don't know if I can stop it. So if you take one particular place, it's multiplying those 9 numbers by the 9 numbers of the filter, adding them up. That, those of you who remember your vector calculus, that's like a scalar product. If I give you 2 vectors, A, B, C and X, Y, Z, the scalar product of it is A times X plus B times Y plus C times Z. So it's just computing the scalar product and it's putting that as an output. There are 2 things that happen. One, of course, there's like multiple things that happen. First of all, you should be very interested in knowing that it's using the same weights even though it's moving over the input. Right? That's not what is required for fully connected networks. Fully connected networks, in different places you might wind up having different weights. That's more general than this. Saying I will use the same weights says I expect some local consistency everywhere in the filter. And in fact, neuroscience basically said that this is a more interesting example, that essentially each of these kernels actually looks like one of these. Let me show these kernels. Yeah, so you can see this convolutional kernel going. Right now, instead of numbers, I'm just showing the picture directly. And so this particular kernel has this part against, there's only one part where there are non-zero weights. Everywhere else there are zero weights. And each patch of the image is a bunch of real numbers. They're just intensities. In fact, there are actually 3 real numbers if you color images, because you have RGB numbers. But if it's just grayscale, it's like a bunch of numbers. You multiply the numbers in the filter with the numbers in the image, taking the dot product essentially. And what you reconstruct is looking like this. Image processing in quad. People knew this is not like completely new. People knew that this kind of things can be done. And so if you can come up with a useful filter of this kind, this particular filter, you get to name that filter. There's a guy called Gabor, and he came up with some class of filters, so they are Gabor filters. And I was unfortunately sleeping, so I didn't have any Lau filters. People had named filters. So they came up with what should these particular kernels be looking like. There are kernels which will look for edges. There are kernels which will look for blobs in the picture, etc. And people were essentially trying to figure these out. So think of that as the way we are doing hand-coded feature extraction. Well, the hand coding is done by coming up with these filters. But if the thing about convolutional networks is these numbers in the filter are just automatically learned, because the numbers in the filters are just weights. In fact, for people who are used to fully connected networks, this is a much simpler problem, because you have much fewer weights, and the same weights are being used in different places. Okay? So the same idea of backpropagation, dropout, and all these things, now except you have a specific kind of a structure for the network, which is this kernel-based moving from place to place. And in the beginning, the numbers in the filters are all randomly input. In fact, they are initialized using Xavier initialization, R batch number. So Gabor is out of circulation. Poor guy has no more name filters anymore. So every neural network, which is 150 layers large, has countable number of unnamed filters that basically nobody got to name, because they just got learned. You see what I'm saying? That's what actually is happening in convolutional networks. Okay? The other interesting point that Hubel and Wiesel pointed out to us is, in addition to Qatar's idea that you are essentially sort of doing this, processing of the image piece by piece by piece, they also pointed out that there seems to be hierarchical structure. That means there is essentially some neurons are looking at what's happening on the retina, and some other neurons are looking at these neurons, some other neurons are looking at the top of the neuron. There are a whole bunch of neurons there, right? They don't all have to be connected to the visual input. They are being connected in this hierarchy. This was again something else to understand. And interestingly, that explains to you why you would wind up having multi-layer convolutional networks. Do you see what I'm saying? Because one level of convolutions gets some features, those then become the inputs for the next level of convolutions, those then become the features for the next level of convolutions, and so on. At the end of all these convolutional layers, in essence, so unlike a fully connected network which looks nice and happy like this convolutional network looks more like this. In fact, you have cuboids here, because really images are not even rectangles, they are rectanguloids, because they're three-dimensional. They have a single image is a rectangle of R values, another rectangle of P values behind it, another rectangular G values behind it, RG. Right? So in essence, the input is this rectangular. Now, I could have used this input this way. I can take all the inputs and put them end to end, and that becomes the input layer. And I could do FC layers. You can actually do this. In fact, before convolutional networks became popular, in neural networks, people were just using FC layers. And theoretically, they can learn everything that convolutional networks can learn. I hope you understand this. Convolutional networks are actually limited in their expressive power. But because they have fewer weights, they can be learned faster. They are likely to have less of overfitting problems. So, in fact, that's how basically you will wind up having convolutional layers, and in fact, there is basically, you have a network which involves essentially, you're taking the spatial nature of the images into account, which reduces the number of weights you have to learn because you're looking at the same weights and applying to different patches of the image. Each convolutional layer is essentially learning a filter that extracts features. The filter weights are themselves being learned by the gradient descent. That's the beauty of it. That's like, the same gradient descent that was taking you, basically filter weights are the weights. That's what they're being learned by gradient descent. One other thing that's actually happening, in fact you saw this here already, is the two things that are happening. In this particular case, depending on the way you are convolving, when you are taking a kernel and shifting it, it becomes an issue of how do you shift it? Do you shift it like one column at a time, multiple columns at a time? Okay? And that brings up these issues of strides and padding. So for example, I can start, one convolution here, next here, that's it. That means the two convolutional operations have no inputs in common. Or they have large number of inputs in common except one power. You see what I'm saying? Those are things that you can change, and those are the ideas of strides. How big a move you are making in the spatial image. Just for a second. And so already, because of the strides involved here, this bigger image became a smaller image here. To the extent it becomes an image. Fewer number of numbers. So somehow you are reducing the size of the input for the next layers. So in some sense, actually, as the convolutional network goes forward, basically inputs become narrower and narrower. As if that is not enough, they also do pooling, which again is something that neuroscience tells us happens. Pooling is, I take, let's say, these four guys, and rather than take all four of them, I take the max of them. And say, you four guys, you will be represented by your average or your max. Typically, you do max pooling. That basically means for every little region, you take every little region of 2 by 2, you get only one number out, which reduces the size even further. So because of which, I'll come back to this later, but let me end this with this. Oh, these are real convolutional networks that are building the image net